All right, so we're finally at video 10. It's the last video of the unit, and this is the fundamental theorem of calculus. So obviously, this is a big deal. There's some really great stuff that we can do in here, and this will actually be a foundation for more that we build on in the next unit. Okay, so the fundamental theorem of calculus basically says this. If you have a function f on a closed interval, so here we go. Part one says if the function g is defined by this, so we need two functions here. So if g is the integral of f for every x that occurs, then g is the antiderivative of f on ab. That part we kind of already know. Part two says if f is any antiderivative, then, and this is the heavy part that we use a lot, the integral of f of x dx is the same as what you would get when you plugged in f of b. So when you plugged b into f minus what you get when you plug in a to f. So remember, a is the antiderivative, or f, excuse me, is the antiderivative. So literally f is the result. So we're saying if you took the antiderivative first, f, and then plugged b in, which is the upper bound minus the lower bound, then you would get the same thing as the antiderivative. Okay, so if I need to change the variable, you guys kind of already know this. We'll talk about this more when we get into it. But if there's a function within a function, when you go to do this antiderivative, you need to do the antiderivative of the function, but also multiply by the chain rule. And so we can look at that a little bit, and you'll see what I mean when we do the example. Okay. Another thing that you should pay attention to is even in odd functions, they actually make doing the integrals easier. So if you're on a continuous integral or integral from negative a to a, so you're going the same amount back as you are forwards from 0. If you have an even function, which means it's the same on both sides, you might already kind of know the answer to this, but you could basically find the front half or the positive side and then just double it because it would be the same thing on both sides. So 2 times the integral of 0 to a, so it makes it a lot faster to do. Or if it's odd, an odd function is a 180 rotation, which means that it is this side is always going to be the positive, where this side is the negative. So if you go the same amount on either side of 0, then these two things would cancel out, giving you 0. Okay. And then the fundamental theorem of calculus part two basically also says this is kind of a shortcut. If you want to take the derivative of an integral, you can plug the function in and you get that x value, as long as this is a constant. So it really is important that that bottom guy is a constant value. But we'll see that happen in action. So let's do some examples. So this guy is going to follow that first one. So instead of having to graph it, which is what we have been doing over the last few days, we can do this algebraically now. So remember, if f, this is little f. So if big F means you've already taken the antiderivative, if big F of 2 big F of 2 minus big F of 0, which is what you get when you plug it into the result for 2, and what you get when you plug 0 into the result, that is also the same as this. Okay, so let's do it. So for this guy, we need to first take the antiderivative. So I'm going to do that quickly. I get x to the 4th over 4, but those 4's cancel. This becomes x to the 3rd, but I would divide by 3, so the 3's cancel. This becomes plus 2x squared, and this becomes minus x. And then we do a notation that looks like this to show that we're going to go from 0 to 2. So this is my result. I'm about to plug in 0 to 2. So I plug in 2 first. So I've got 2 to the 4th minus 2 to the 3rd plus 2 times 2 squared minus 2. I think you get the idea here. So let's see what we get. 16 minus 8 plus 8 minus 2. So I end up with 14 minus what I get when I plug in 0. Now the nice thing about that is I get 0 minus 0 plus 0 minus, you get the idea. So I basically just get 0. So I get 14 here. Okay, so let's look at an example where we need to do the antiderivative, and hopefully this is coming back. Since that bottom is a function within a function, we're probably going to use U-substitution. Okay, so we're going to solve this. We'll take the derivative of both sides. We get negative dx. We end up with negative du. This is a little forethought happening right here, but okay. Now back over to the problem. Here's the deal. When I change this relationship to a u, I have two options technically. I like to do the first option. So this is really 2 over root u dx. I'm going to put my integral here for a second. There's a reason I'm not filling these in. Over here, I can replace the dx with a negative du, and I technically could bring that 2 out if I want, and so I end up with this. Now, here's the issue. When you change your integral into something in terms of u, you technically change the integral bounds because these bounds related to x, but you can change those to work for you. So here's what you need to do. If you want your new bounds with respect to u, then you can say, okay, solve this for your new values. So if x is 0, for example, which is my lower bound, what is u? Well, 4 minus 0 gives me 4. So my new lower bound is 4. Okay, what about when x is my upper bound? 3. Well, plug that in. So u equals 4 minus 3, which gives me 1. Okay, this is going to be the same result. Now, obviously, if you're me, you're probably looking at this going, well, this is the bigger number, so flip it and make it 1 to 4, but of course that would make the whole thing negative, which would make this back to a positive 2. I'm going to go ahead and make this u to the negative 1/2 at the same time. So let's do the antiderivative. My antiderivative here then is u to the positive 1/2 divided by 1/2, which is times 2, and I'm going to go from 1 to 4. Now, the cool thing about this, because you changed your bounds to relate u, you don't have to plug u back in. These bounds, 1 and 4, already apply to u, so you don't have to plug all this business back in. That's great news. So here we go. So that means I have 4, and then I'm going to take u to the 1/2, which I'm going to do my upper bound first. So I'm going to do 4 to the 1/2, and then I'm going to subtract what I get when I plug in 1, which will be 4 times 1 to the 1/2. So again, I didn't have to replace the u back in because I changed my bounds to work for u. Okay, so then I end up with 4 times 2 minus 4. So I end up with 4 for my final answer. You might need to watch that again. Okay, in example 3, let's see, let's do it. So I'm going to have to use my U-substitution. So here I go. My du is 2dx. If I go back to the problem, I'm going to leave these open for a second. I get sine of u dx, which means I'll need the 1/2 du. So I'm going to plug that in. So I'll bring the 1/2 out. Integral sine u du. But again, since I want to do everything in terms of u, I'm going to go over here and go, okay, let's do x equals 0. Well, if I plug in 0, I get 0. So my lower bound is still 0. If x used to be, my upper bound used to be pi over 4, but I'm going to plug that in. So I get 2 times pi over 4, which is actually pi over 2. So my upper bound will be pi over 2. Now I can do the rest of this problem in terms of u. I don't have to go back. So my integral of sine of u is negative cos u, and I'm going to do that from 0 to pi over 2. So here we go. We get negative 1/2 cos of pi over 2, and then I'm going to subtract what I get when I take negative 1/2 cos of 0. Don't forget the minus in between. If you want, you can make this a plus now. That's fine, or you can wait. So this is negative 1/2 cos at pi over 2 is 0. Plus now 1/2 cos at 0 is 1. So I just end up with 1/2. Okay, now in example 4, this is the second half. Now I'm taking the derivative of an integral. Now remember, typically these would cancel out, but something interesting happens here. So you can't just cancel these out and, just say, oh, it's just sine of t squared dt. It doesn't work like that. We do have a rule that says as long as this is x and as long as this is a constant, then this would basically just become, since you're doing the derivative of an integral, these two things cancel out and you just get sine of x squared. Now, if you wanted to look at this, you could do it. Absolutely. You could do the antiderivative first. So I would do the antiderivative. I would have to do a little bit of chain rule here, which I can totally do. So I'd have u equals t squared. I'd have du equals 2t dt, or 1/2. So I'd have 1/2 from 0 to x of, let's see, sine of u du. In this one, I'll show you how you don't have to use the U substitution if you don't want to. So in this one, I would end up with, let's see, negative 1/2 of cos of u. I'd plug the u back in. So this is an example where I am plugging it back in. And then the reason if I plug it back in, I can use the u and the x. So what you notice here is I end up with negative 1/2 of cos of t squared, or I'm sorry, x squared for my first part. And then the other one, I would plug in minus negative 1/2 cos of 0. And so this gives me, let's see, this one I would have to do the chain rule. So I'd do negative 1/2 sine squared. Notice I made that positive because the derivative of cos becomes negative sign. So that became positive of x squared. I'd have to do times chain rule, which is times 2. This is a constant, so that just would become 0 when I do the derivative. And so I just get sine of x squared. But wow, was that much easier to just use the fact that these two cancel out. And as long as this is an x, you get just x squared. Now we'll talk about how it affects it if it isn't an x squared in a moment. So what happens if it's an x squared? Well, if I want to do, first of all, this is g, which is an integral. They ask for g prime. That means they want the derivative of this. So that now we're back to the same place we've been. Well, the way that this works is you can treat this as, remember we said a second ago, as long as this is a constant, and that has to do with the fact that when you do this minus this, and so that's a constant. You end up with e to the x squared, right? Because that would be what we would plug in, and then times the derivative of this upper bound function. So the derivative of that upper bound function is 2x. So my final answer is 2x e to the x squared. Now, if I wanted to do this the long way, I could do the integral of this inside. So the integral of e to the t is just e to the t, and I would do it from 0 to x squared. And that would be e to the x squared minus e to the 0, which is 1. But then remember, we want the derivative, and we want it at 2. So I actually have to plug 2 in down here, but I'll do that in a second. So the derivative of this, remember, the derivative of e to the x squared, I'd have to do chain rule. It'd be e to the x squared times the derivative. Aha, do you see now where that comes into play? And then because this is the derivative of a constant, it's just minus 0. So that's gone. Okay, but then for both of these, I need to plug in a 2. So I would have my final answer be 4e to the 4th. Okay. In example 6, I'll do the shortcut version. So if I want to do the derivative of this integral, then I know that I can plug in my upper bound as long as this is constant. So I have ln of x cubed, and then times the derivative of x cubed, which would be 3x squared. So pretty easy. Now, this last one, I just want to show you how to do it with the calculator, and it's actually really easy. So let me bring up my calculator. Now, remember, if you're going to use trig functions, you need to make sure that you are in radian mode. So I am in radian mode. I'm going to go back out, and I'm going to click math. So I hit the math button. I'm going to go down here to my function integration, and I can put this in. So I'm going to put in negative 0.2 up to 0.73. So you should be testing this and trying this in your calculator for yourself. X cubed, making sure you're plugging in everything very carefully, minus cos of x squared. Now notice when I did a cos, it added a parentheses, so I need to close off that parentheses. Be careful, all those things matter. And then of course I'm going to say dx. I hit enter. It's going to do all the work for me. I can round to 3 decimal places, negative 0.655. So the calculator ones are of course easy, and they're going to give you all sorts of nasty functions because if you can type it into your calculator, then that's, not hard to do. So, okay, we've got a nice problem set that's coming up, and then we will be working on this for a few days in class, and then we'll take a test soon. Okay, see you in class.